Swayam Prabha. Digital India. Educated India.
Welcome to this lecture number 16 of the NPTEL course in fluid mechanics for chemical engineering undergraduate students. Today we are going to discuss the integral energy balance, and we started this discussion very briefly in the last lecture. And as I told in the last lecture, all the fundamental integral balances in fluid mechanics, namely mass, momentum, energy, they rest on a fundamental physical principle. For example, the integral mass balance came out as a consequence of the principle of conservation of mass, and the integral momentum balance came out as a consequence of the Newton's second law of motion. Okay. Now, we are ready to discuss the integral energy balance, and the fundamental principle that helps us to derive the integral energy balance is the first law of thermodynamics. Okay. The first law of thermodynamics is essentially a generalization of the notion of energy, okay, to systems such as fluids. Okay. So, the notion of energy is familiar from mechanics, where you had potential energy and kinetic energy of a macroscopic object like a sphere. Okay. So, for example, you could say that a sphere is at rest, okay, if it is on top of a table, let us say, and gravity is this acting like this. This is the ground level. Okay. Now, you can tip over the sphere, and the sphere acquires, it moves, and the motion, the energy associated by virtue of its motion is half mv squared, where m is the mass and v is the velocity. This is called the kinetic energy of the sphere, which is associated with the motion of the sphere. While when the sphere is at rest, we say that the sphere has a potential energy by virtue of its elevation from the ground level. Okay. So, if you just tip over the sphere is going to fall down eventually, and it is going to come to the ground level. Okay. Now, if you ask the question, how am I going to bring the sphere back up to the same level, you have to do work. So, that is, you have to apply a force, okay, on the sphere. That is, we have to apply a force, okay, over this distance h, let us call this distance as h, okay, and the application of the force over a distance h will amounts to doing work on this sphere, so that you can bring it back to its original elevation. Okay. And the force that you apply is exactly mg. So, the work that you have done in order to bring the system back to its original state, the sphere back to its original level elevation, is the same as its initial kinetic energy. So, this is the work energy equivalence principle in mechanics. Principle in Newtonian mechanics, which deals with objects such as spheres of macroscopic sizes and so on. But now we are in the domain of discussing energy conservation for systems like a beaker of a fluid. For example, you may have a piston cylinder assembly, okay, and you may have a gas, okay, a dilute gas such as air present inside the piston cylinder assembly. Now, let us imagine that you have this gas, okay, and initially the gas is at a given volume, okay, which is denoted by V1 or VA, let us call it VA, and the temperature, let us say, is constant, okay, or let us even insulate thermally this piston cylinder assembly, okay, and it has a temperature TA. Now, imagine putting in a weight, so that this piston now moves. So, there is a weight that is acting, there is a force that is acting. So, you compress the piston, so that you are now in a new state B with volume VB and temperature TB. Okay. Now, you have done work on the gas, because you have applied a force and you have moved the piston over a distance. So, the volume of the gas initially which was VA is now greater than the final volume VB. Okay. So, you have certainly done work on the gas. Now, initially the gas is stationary. Now, after doing work, if you leave the gas for some time, it will again come to rest, that is there will be no visible macroscopic motion of the fluid that is present inside the piston cylinder assembly. So, this means that you have done work was certainly done on the gas by virtue of the weight or the force that you apply over a distance. Okay. Now, we want to generalize the principle of energy work equivalence to systems like this. Okay. In the previous case, when we did work on the sphere by lifting it up, we said that the work done has gone on to increasing the kinetic energy of the sphere. Okay. Now, what has happened to the work done? Okay. So, this system, a system of gas present in a piston cylinder assembly, is not a single sphere, it has many fluid molecules. Okay. So, in the continuum description, okay, we think of this system as we think of this collection of fluid molecules, gas molecules, as a system, okay, which is prescribed by a variable such as its volume and its temperature. Okay. Now, you have done work on this system and you have compressed it. What has happened to the work that you have done? Well, since you have completely insulated the system, okay, this work that has been supplied to the system clearly has not gone to increase the potential energy of the system, nor has it increased the macroscopic kinetic energy of motion of the fluid molecules of the fluid, because initially the fluid at rest and finally also the fluid is clearly at rest. So, what has happened to the work is that it has gone on to increasing the internal energy of the system, and internal energy is a new concept that comes from thermodynamics, and it has a role to play even in fluid mechanics, because we will see that these notions or principles are helpful while understanding the principles of conservation of energy and energy balance even in fluid flows. Okay. Internal energy is that part of energy associated with microscopic or molecular degrees of freedom. Okay. So, what has happened is that when you do work, initially the gas is at a temperature Ta. Now, from elementary kinetic theory that you may be aware from physical chemistry or some physics courses earlier, you know that the temperature of a gas is related to the average kinetic energy of motion of the molecules. Okay. A gas is of course comprised ultimately of molecules, and these molecules are always in constant motion, even though on an average the gas appears stationary or static, but microscopically at a molecular level all the molecules are moving at a very high velocity, and the temperature is a measure of the average kinetic energy of motion of the molecules. When you apply a force over a distance, thereby doing work on the piston, you are compressing the gas, and the work that you have done has gone on to increase the average kinetic energy of motion of the molecules, and therefore, it has gone on to increase the temperature. Okay. So, this energy of motion, kinetic energy of motion associated with molecular degrees of freedom is essentially characterized as the internal energy, that is the energy that is internal to the fluid, that does not manifest in macroscopic senses such as potential energy or kinetic energy, but it is actually a characteristic of the molecules that comprise the fluid, is called the internal energy. So, what we have said so far is that when you have an insulated container, when you do work on a gas by placing a weight, the work that you do has increased the internal energy of the system, because clearly the gravitational potential energy has not changed, nor has the kinetic energy changed, because the gas is stationary macroscopically speaking, there is no visible bulk motion of the molecules. So, internal energy, work done can change internal energy. This is an experimental fact of the molecules of the gas. Okay. Now, is this the only way to change internal energy? Okay. The answer is no. We can also change internal energy through an entirely different route. Okay. So, imagine in state B, okay, now the gas is in state B with volume VB, temperature TB. Now, imagine removing the insulation, the thermal insulation, thereby you are now allowing the beaker or the piston cylinder assembly with gas present at temperature Tb to transact energy with surroundings by virtue of transfer of heat. We know from experience that whenever you have a hot body in present in a cold atmosphere, you know that the hot body will eventually cool down, and there is a transfer of energy, that is heat transfer, that happens from the hot body to cold body. Okay, that is what will happen, and eventually you will have the system, okay, with temperature Tb and volume V, temperature Ta, because it has lost all the energy to the surroundings, but volume is still Vb. Now, imagine heating the system using a burner such that you have provided enough energy, so that eventually you are now reached a state where, okay, you have reached a state where you have temperature Tb and again volume Vb. Okay. Now, once you have reached temperature Tb, you can insulate the system, and this will be identical to the state B. Okay. So, the state B that you had here and the state B that you had here are identical, because they have the same volume and same temperature. But what is important to understand is that the way you have reached the state B is entirely different in these two cases. In the first case, you compressed a gas present in an insulated cylinder from an initial state of temperature Ta, and then you did work, okay, by applying a force, and that resulted in a new state with temperature Tb and volume Vb. Now, you remove the insulation, thermal insulation, and allowed the gas to cool down to the ambient temperature Ta. Again, you reach Tb, the previous state B, through an entirely different process, namely by transacting heat by exchanging heat from surroundings by let us say having a burner. Okay. So, what is important, and this is the important lesson from first law of thermodynamics, is that fluid systems such as a piston cylinder assembly containing gas, macroscopic system which innumerable molecules, they are characterized by not just by their gravitational potential energy or their macroscopic kinetic energy of motion, but they are also characterized by their internal energy, and this internal energy can be changed by doing work, as we have seen, or by exchanging heat. Okay. So, this is the statement of first law of thermodynamics, that first law thermodynamics. It states that the change in energy of a system is equal to the rate at which heat is transferred to the system, and the amount of heat transferred to the system and amount of work done by the system. So, let me write down all these things in words, and then we will discuss the sign convention. Okay. So, this is change in total energy of the system is equal to amount of heat transferred to the system this is the amount of work done by the system on the surroundings. Okay. Let us understand the implication of this equation from the example that we just did. Initially we said that, so let me write this equation again, dE is del Q minus del W. In the first case we said that we had a system where you had TA VA and you insulate the system. When you insulate the system, then there is no heat transfer with the surroundings, so del Q is 0. So, the change in energy is equal to minus del W. If you do work on the system, then del W is negative. So, negative of negative is positive. So, the energy increase is positive, that is the system has increased its energy, which is what we said, and it makes intuitive sense as well. Now, if the system does work, okay, so let us imagine another case, again insulated. If the system does work on the surroundings, it is going to lose energy. So, dE will be negative. So, if work done is positive, if delta W is positive, that is system is doing work on the surroundings, then the system will lose its energy. Okay. So, that is the meaning of the sign convention. So, there can be other sign conventions. So, you must be careful about other sign conventions. The other common sign convention is that heat transfer to the system is positive, as we said here, but also work done on the system is positive, in which case the first law will read as dE is dQ plus dW, del Q plus del W. Another point I will just mention in passing, but not spend too much time on, is the nature of the differentials here. dE in thermodynamics is called an exact differential, whereas del Q and del W are called delta of something is an inexact differential. This is because, okay, these quantities such as work and heat, they are not functions of, the amount of work that you transact depends on the path, the way in which you go from state 1 to state 2, okay, whereas the energy is a function only of the initial and final states. So, quantities like energy, temperature, pressure, they are called state functions, because they just once you know the thermodynamic state of the system, you have, let us say you have temperature and pressure, you can say what its density is, what its energy is, regardless of how the system was prepared. Okay. It is independent of the history of the process by which you have reached that particular state. So, quantities such as energy, pressure, temperature, they are called state functions in thermodynamics. Okay. Whereas work and heat, clearly you can reach the same state by doing completely work or by doing heat. So, clearly work and heat are not state functions, it depends on how you carry out a particular process. Okay. So, they are called path functions. Therefore, you cannot write work or heat as an exact differential. So, they are denoted by a delta, the infinitesimal work done is denoted by delta rather than d, because it is not an exact differential. But more of this will be done in the thermodynamics course, but we will not do this right now. We will rather proceed to generalize this first law, which we initially wrote for a finite amount of heat or work that is transferred to or from the system, and we related that to energy changes in the system. But in fluid mechanics, we do not look at systems where you look at a finite amount of heat transferred and then you take out a work in one shot. Things happen continuously in many engineering operations. So, we need to generalize this to a form in which we talk about the rate at which energy is changing in the system, to the rate at which energy heat is transferred to the system, and to the rate at which work is done by the system. So, we are going to generalize this to a flowing system where things change with time continuously. So, the rate of change of total energy of the system is equal to the rate at which heat is transferred to the system minus the rate at which work is done by the system. So, Q dot is the rate at which heat is transferred to the system, and W dot is rate at which work is done by the system. This is the rate at which energy of the system changes with time, rate of change of energy of the system. Okay. Now, What is the energy of the system? The energy of the system, of course, comprises of the internal energy plus potential energy, macroscopic potential energy by virtue of its elevation with respect to a datum or a ground level, plus macroscopic kinetic energy. Now, we want to use Reynolds transport theorem to convert the rate of change of energy of the system to the rate of change of energy in the control volume. So, remember in Reynolds transport theorem, we always write E system as volume of the system rho E dV, where E is E divided by mass, energy per unit mass. Small e is the total energy per unit mass. So, small e is nothing but the internal energy plus unit mass plus the kinetic energy plus unit mass. Kinetic energy is half mv squared. If you divide it by mass, you will get half v squared, plus the potential energy per unit mass. The potential energy is mgz, where z is the elevation. So, this is Ke per unit mass. This is potential energy per unit mass. Okay. So, this is, and v square is the magnitude square of the magnitude of the velocity is given by the vector velocity v dot v. Okay. So, we want to now generalize this to a control volume kind of a situation formulation. Okay. In order to use the Reynolds transport theorem, we have to say, remember the Reynolds transport theorem, we have to use dN dt of the system. Okay. So, this is nothing but d dt, this is the Reynolds transport theorem of Cv dV, okay, rho eta plus integral over Cs, okay, rho eta v dot n dA over all the control surfaces. This is the rate at which a quantity like mass, momentum, energy changes within the control volume. This is the flux term that takes mass, momentum or energy inside or outside the control volume by virtue of flow within flow to into and out of the control volume. Okay. So, now we are going to say n is nothing but n is capital E and eta is E by mass, which is E small e. So, the rate of change of energy of the system as written in terms of the variables relevant to a control volume is rho e, this is the local rate of change present in the control volume, plus the flux term rho e dA. Okay. This is something that we have seen frequently before for mass conservation and momentum balance. So, it is the same here. Now, remember when you do the Reynolds transport theorem, you identify the control volume and you say that the system and control volume coincide at time t0, system at time t equal to t0, system is the same as control volume, but at a later time you know that the system is going to move out of the control volume. So, this is t naught plus delta t. Okay. The system has moved out of the control volume, but we are now looking at the instantaneous rate of change of energy of the system when the system and the control volume are the same, okay, at some time t naught. So, if you want to apply the first law of thermodynamics at that instant when the system and the control volume of the same are the same, then the rate at which q dot minus w dot is the rate at which work is done, heat is transferred, and the rate at which work is done for the system is the same as that for the Cv, because the system and the Cv coincide at the time t equals t0. So, the first law of thermodynamics, the rate form of the first law of thermodynamics becomes, okay, this is equal to d dt integral over Cv, okay, rho e dV plus integral over the Cs rho e, this is the flux term. Okay. Now, this is the rate at which work is done by the system, so at the Cv, rate of work done by CV on surroundings rate at which heat is transferred to the CV. So, this key thing is you should notice this is by CV on surroundings, this is to CV on surroundings. This is very important when we do the problems in using energy balance. Now, that completes the statement, the formal statement of the energy balance, but now of course, we have to sort of write this in terms of many contexts that are relevant to fluid flow. Okay. So, first is what is the rate at which work is done by CV. Okay. What is the rate at which work is done by CV on the surroundings? Okay. That is positive when work is done by the CV on surroundings. When work is done on the CV, it becomes negative. What are the various types of work? Okay. So, in order to understand and appreciate this, let us imagine a typical process that will happen in many fluid flow equipments. Okay. So, let me draw a container in which fluid is coming in and going out, and there may be a shaft, okay, and which has rotary blades which rotate by virtue of the rotation of the shaft. Okay. And this is the area, cross sectional area of the shaft CS area, cross section area. So, fluid is coming in like this and going out like this, and let us now draw what the CV is. Sorry, let us now draw the CV by demarcating the CV from the surroundings using the control surface. So, the line marked in red, the dotted line, is my control surface, and whatever is presenting whatever is present inside is my control volume. Fluid is continuously coming in and going out. Okay. Now, what are the various types of work? So, there is an area here where the control surface is cutting across, where fluid is flowing in, that let us call that area AF, where the flow is happening. The rest of the area let us call it AI, and of course, this area where the control surface is cutting across the shaft which is rotating is AS. These are the three different types of areas that we can distinguish. So, the rate at which work is done is due to various reasons, work done by the shaft work. So, whenever you have a shaft that is rotating, okay, and when the CV is cutting across the shaft, there is a stress on the solid surface and there is a force therefore, and since there is the shaft is also rotating, that means that there is a force that acts with a velocity, okay, and therefore, there is a work done, okay, because of this rotation of the shaft. Okay. If the shaft rotates and does work on the CV, that becomes negative. On the other hand, if the CV rotates the shaft and therefore, the work is done by the CV on the surroundings, delivering useful work to the surrounding, then it becomes a positive quantity as per our convention. Now, the rate at which work is done by normal forces on the CV, on the CS, that is control surface, the rate at which work is done by shear forces, and if there are other contributions, the rate at which work is done by other reasons. Okay. Now, remember one important fact is that a force does work only if the element on which it acts moves in the direction of force. Displaces in the line of action of force. What this means is that if you look at, there could be fluid flow here, by virtue of which there could be a stress here due to this fluid flow, but this control surface is stationary, it is a rigid stationary boundary, okay, in which case there is, even though there is a force acting, there is no motion, therefore, there is no work done. Okay. So, there is no work done on the internal area AI, that is what we try to conclude from this simple idea, that a force does work only if the element over which it acts moves in the line of action of force, okay, it displaces. Okay. So, there is no work done in AI, the internal area. Okay. Now, if you look at the shaft work, if you look at AS, okay, then there will be a stress. I am just sort of, so this is the CS that is cutting. There will be a stress in the solid surface over which the control surface is cutting across, okay, and therefore, there is a shear stress and there is an associated motion, a rotatory motion. So, there are forces associated with, there is work, rate at which work is done either by the system on the surroundings or by the surroundings on the system whenever the control surface cuts across a rotating shaft. So, there is a rate at which work is done, and that is called the shaft work. Okay. So, that shaft work is what is denoted as W dot S or W dot shaft. Okay. This is because of the rotating shafts which may either deliver work to the system or which may take work away from the system. Okay. So, work output from the CV is considered positive. This is an example of a turbine which delivers work, okay, and work input to the CV is negative. It is an example of a pump where you have to expend external energy, okay, to increase the pressure head of a fluid. Okay. Now, the shaft work, and then you have work done by normal and shear stresses. So, we look at this case by case, work done by normal and shear stresses. Okay. So, the rate at which, so work done is simply F dot ds. Okay. The rate at which work done is del dw del t, limit del t going to 0 is nothing but F dot v. So, let me denote all vectors with an underscore F dot v. Okay. So, F is nothing but the stress vector that is acting on the surface dotted with v, but you have to integrate it over the entire control surface, okay, where there is flow as well as there is motion. So, remember that there is a work done only if there is a motion on the motion of the element on which stresses are acting in the line of action of the force, as we have been repeating. Okay. Now, sigma is nothing but sigma normal, which is in the direction of the unit normal, plus sigma tangential or shear, which is in the direction perpendicular to the normal. Okay. So, the rate at which work is done, W dot, due to stresses, fluid stresses, is nothing but sigma n times V dot n dA over the control surface plus integral sigma tangential dotted with V dA. Okay. Now, this is the normal rate at which work is done by normal component to the stresses. This is the rate at which work is done by shear or tangential component to the stresses. Okay. Now, this is the work done by on the entire control surface. So, this is the work done on the entire control surface by the shear stress. So, work done by the control surface on surroundings is the negative. Okay. So, this is the work done on the CV. So, I am sorry. So, this has to be, this is the work done on the CV by the, okay, this is the work done on the CV. If you want to know what is the work done by the CV on the surroundings, so work done by the CV on the surroundings is nothing but minus, so the normal component of the work W dot normal is minus the negative of whatever we have written, because this is basically the work done on the CV, but the work done by the CV on the surroundings is the normal component, due to the normal component of the stresses is this, and due to shear is nothing but minus sigma T dot V dA. Okay. Now, what are the various components to the shearing forces? There are three types of areas. One is the area over shafts, sigma T dot V. This we already have accounted it as the shaft work. Okay. So, this entire thing is called the shaft work, okay, minus integral sigma T dot V dA over solid surfaces. This is the AI part minus A flow part sigma T dot V dA. Okay. Now, over the entire AI internal area surface, which we just, if you look at the general figure that we drew, in the over the entire internal area surface, velocity is 0 because the fluid is stationary. So, even though there is a stress that is acting, there is no work done because the velocity is identically 0. So, this drops out. This was already taken into account as shaft work, W dot shaft. So, the only thing that is left for us to understand is this. Okay. But imagine that if you have, so where the flow area is where the inlet or outlet is actually present. Okay. This is A flow. So, if velocity is acting like this and the tangential stress act in the direction perpendicular to the velocity, if you choose your control surface such that the velocity is normal to the control surface, okay, then V is perpendicular to the sigma stress, tangential stress. So, V dot sigma T is 0. So, by carefully choosing the control surface, you can actually have the tangential stress on the inlets and exits to be 0. So, we can, by carefully choosing the control surface such that the velocity is normal to the control surface, then the tangential component to the sigma T stress is acting perpendicular to the velocity. So, the stress is acting like this, velocity is perpendicular. So, there is no, the dot product is 0 of these two vectors. So, the shear component to the work, there are three types of areas that we said. One is, let me just draw the internal area, the flow area through which fluid is entering and exiting, and the shaft area which is cutting across the control surface. So, there are three contributions to the shear work. One is due to the shaft work, which we have already separated out, okay, so that we do not have to include. One is due to the work done at the internal areas that we said is 0, because even though there is a stress, there is no velocity. So, sigma T dot V is identically 0. And in the third case, we had the work done at the flow areas, and there it is 0 because the stress and the force and the velocity are orthogonal or perpendicular to each other. So, W dot shear is 0 because we have already taken into account the shaft work separately. Once we understand this, and the normal component to the work is nothing but integral minus integral sigma n. This is the work done by the CV on the surroundings, okay, CS sigma n V dot n dA. This is the work done by rate at which work is done by CV on the surroundings due to the normal component of the stresses. We will see a little later that the normal component to the stress comprises of both a pressure which is acting compressively, if you know. So, sigma n is minus P because if you take a surface with unit outward normal n, pressure is acting in the direction of minus n. Okay. P, the pressure acts is the direction minus n. Okay. So, sigma n is P, okay, minus P, and then you also have some viscous shear stresses acting in the normal direction. Viscous, let us should not call it shear stresses, viscous normal stresses, but these are usually negligible, they are neglected. So, sigma n is minus P to a good approximation, So, W dot normal is nothing but, if I substitute this here, the two negative signs will cancel out. So, P V dot N dA over the control surface. Okay. So, the total rate at which work is done is nothing but the shaft work when the control surface cuts across rotating elements such as shafts, which will typically convey energy in or out of the system, convey work in or out of the system, times P V dot N dA. So, the first law of thermodynamics for a control volume eventually becomes, okay. So, eventually becomes Q dot minus W dot shaft minus integral P V dot N dA Cs, okay, and minus W dot shear. In general, we said that that can be carefully, by choosing the control surface appropriately, we can set it to 0 exactly. So, this is equal to the rate at which energy is changing, and that is the rate at which energy is changing within the control volume plus the rate at which energy is entering or exiting the control volume by virtue of flow. Okay. This is on application of Reynolds transport theorem. Okay. Now, I can take, if you look at these two terms, they are identical. So, I can bring this term out here to write Q dot minus W dot shaft is d dt integral rho E dV plus integral E plus P by rho times rho V dot N dA. Okay. This is something I can do by just multiplying and dividing by rho. I can do this very easily. Okay. So, where E, if you remember, is the specific energy, that is energy, total energy per unit mass, which is the internal energy plus unit mass plus the macroscopic kinetic energy plus unit mass plus the macroscopic potential energy per unit mass. So, we further write this in the following manner: Q dot minus W dot shaft is d dt integral Cv, this is Cs, Cv rho E dV plus integral Cs E, I am going to write it as U plus, then I also have a P by rho plus half V squared plus Gz rho V dot N dA. Now, in thermodynamics, this quantity is called the enthalpy per unit mass, specific enthalpy. P plus U plus P by rho is called the specific enthalpy, okay, enthalpy per unit mass of the fluid. Okay. But that is in thermodynamics. Okay. But in fluid mechanics, we normally do not do this for a specific reason. So, I will come to that in a minute. Okay. So, remember that we are choosing the control surface, choose control surface such that V is perpendicular to N at in and outflow, such that W dot shear is identically 0. That is, at the inlet V dot N is minus V and V dot N is V at the outlet. So, you should always choose your control surface. The velocity vector is perpendicular exactly to the, or the velocity vector is exactly perpendicular to the control surface, so that there is no component in the direction parallel to the surface. Okay. So, that is something that we can always do when we choose our control surface. Okay. This is V, this is N at the inlet. So, V dot N is minus V, this is V, this is N at the outlet. So, V dot N is plus V. Both the vectors are pointing in the same direction at the outlet, whereas both the vectors are pointing in the opposite direction at the inlet. Now, so we can write further d dt of integral rho E dV over the Cv is nothing but rate at which heat is transferred to the system minus the rate at which shaft work is done by the system minus integral over all outlets. I am separating outlets and inlets now, E plus P by rho, rho V dA plus integral over all inlets, E plus P by rho, rho V dA. I am taking into account this minus V dot n as minus V at the inlet and plus V at the outlet. That is why you are getting two different signs at the inlet and outlet. Okay. Now, I am going to do one more thing. I am going to assume the flow is steady. I am going to simplify this. Flow is steady, which means that d dt of rho E dV is 0, because nothing changes with respect to time within the control volume. So, all you will get is integral over Cs outlet E plus P by rho, rho V dA is integral over Cs inlet rho V dA plus Q dot minus W dot shaft. Okay. If the flow is, if you have uniform flow at the inlet and outlet and uniform properties such as energy and so on, then I can trivially do the area integral to write summation over all outlets E plus P by rho times rho V A is summation over all inlets E plus P by rho times rho V A plus Q dot minus W dot shaft. Okay. In a steady flow, rho V A in is equal to rho V A out, that is mass conservation, that is equal to rate at which mass is entering or leaving the system. So, if I divide by m dot throughout, I get summation over outlets E plus P by rho is summation over inlets is equal to E plus P by rho, okay, plus Q dot by m dot minus W s shaft by m dot. Now, this is the rate at which heat is transferred to the system, to the CV by the surroundings. This is the rate at which mass is flowing in. So, this combination is denoted by small q. This is the heat input to the CV per unit mass. And this is the shaft work output per unit mass. Okay. So, that is the, so these are given special names, small q and small, there is no rate associated with it, because you are dividing the rate at which heat is transferred by the mass flow rate, and likewise the rate at which work is done by the system or the CV by the mass flow rate. So, that they are no longer rates. This is the rate at which heat is transferred per, this is the heat transferred per unit mass and the work done by the CV per unit mass. There is no rate associated with it anymore. So, summation over all outlets U plus V squared by 2 plus GZ plus P by rho at all outlets is summation over all inlets, the same quantity this is at outlet, this is at inlet, plus q, small q minus small ws. Okay. Now, this is the energy of the fluid at the outlet, as in some sense this is the energy of the fluid at the inlet. Why is the energy of the fluid at the outlet changes? It could change from the energy of the fluid at the inlet, because you are transferring heat in the CV or you are taking out work from the CV. Okay. Now, this is true for any fluid, but in fluid mechanics, at least in this course, we will now restrict ourselves to incompressible fluids, where rho is a constant, that is, it is independent of pressure. There is no change in the density of the fluid because of the fact that there are pressure changes in the flow. So, the pressure becomes a mechanical variable, it is no longer a thermodynamic variable. That is, the pressure, since the pressure changes do not alter the change in density, do not alter the density of the fluid, that means that you cannot take the pressure to be a thermodynamic pressure, it is simply a mechanical pressure. So, it is often convenient to keep all the mechanical quantities together and to move the thermodynamic quantities, summation V squared by 2 over all outlets plus Gz plus P by rho is summation over all inlets V squared by 2 plus Gz plus P by rho, this is at outlet, this is at inlet, plus Q plus U out minus U in, okay, or let us put it minus Q, okay, minus Ws, small ws, this is not a rate, okay. So, it is minus U out U minus U in minus Q, okay. So, this is valid for incompressible fluids. Now, because we are setting thermodynamic variable aside from the mechanical variable, okay, and we will stop at this point and we will try to give a physical meaning for all these terms in the next lecture of our course.